Okay.
Okay, good afternoon. So today we're going to talk about calculus of variations. Okay, so calculus of variations is used to to get the extremum value of a certain function under certain conditions. Okay, so the basic problem for calculus of variation is this, which is the basis of all applications of calculus of variations, one of which is the Euler-Lagrange equations. Okay, so the basic problem for calculus of variation is we should determine the function y of x such that the functional integral j, where j is the integral of the function as a function of function f as a function of y, which is a function of x, function of y prime, which is the first derivative of y with respect to x, and x dx from xi and x1 to x2. Okay, so again here y prime is the derivative of y with respect to x. So right now we're just going to use the variables y, x, and derivative of y with respect to x as our general variables. Then we're going to extend this to the Euler-Lagrange equations. Okay, so what are we going to do here is that the basic problem is that determine the function y such that this functional integral, okay, is an extremum. When we say extremum, it's either minimum or maximum. And that is precisely what calculus is doing. Specifically the differential calculus. So you take the derivative, you're basically taking the slope of the graph at certain positions in x, and there you will know if the function at that position x is an extremum by equating it to 0. So this is what we're exactly going to do here. But instead of just getting the derivative, we're going to deal with the variations with the function. So for example, we have this function y is a function of x. Okay, and we said that we have 2 points. Identify 2 points, x1 and x2. Okay, so between x1 and x2, there's a function. This is our extremum, or our function. This is our extremum path. And what we don't know this path right now. This is our goal. Okay, so the point here is that we're going to define this function f, and we're going to take the extremum of that f in order to get 1. Okay, so as an example, let's say this is your extremum value. This is our goal. Okay, but we only know the point x1 and x2. So what we're going to assume here is that we're going to put some variation in this function and try to minimize that in order to get the extremum function that we want to identify. So for example, instead of going this path, you want to get this path. So this path is what we call your varied path. This varied path is defined as y. This is our function. Oh, sorry, this is y. Okay. So what we're going to do here is the varied path is y plus some function n, which is a function of x, times alpha. This is our y as a function of alpha and x. So what we have here is that if this is your extremum value, this is what we want to get. And then we want to vary that by this amount, by alpha nu as a function of x. Okay, so this variation is alpha nu x. Okay, so if we're going to identify another function, variation of that function, let's say this. This is another variation. Let's say this is alpha 1, this is alpha 2. Okay? So if you're going to graph this, okay, if you're going to graph the variation nu, or the variation alpha nu, this is what we're going to have. And this is x, and this is x. Okay? So for example, this, the difference between nu, alpha nu x is y minus y. So this, for example, at x equal to 1 and x equal to 2, nu sub x1 is equal to nu x2, and they're equal to 0. Because there is no variation at x1 and x2. But once you progress from x1 to x2, the variation increases in such a way. Let's say this is alpha 1 nu 1, and then let's say this is alpha 2 nu 2. Here we're taking the absolute value. Okay? And the goal is we want to minimize this variation in order to get our goal function from this varied function. Okay? So, here we note that ky alpha x would approach y x as alpha approaches 0. So this is what we're actually going to do. Okay, we want to approach alpha to x so that y will approach y as a function of alpha and x. Okay? And nu x is some arbitrary function of x. And we're not going to deal with what is this specific function. But we're going to use this function to get our solution. Okay? So therefore, if from this functional derivative, this functional j becomes from x1 to x2, this is the integral of the function f of y alpha x, y prime, alpha x, and x dx. So this notation, semicolon, indicates that x is independent of y and y prime. Okay? But y and y prime is dependent on x. Okay? So if we're going to apply this to the Euler-Lagrange equation, y will represent the position, y prime will represent velocity, and x will represent time, where time is independent of the position and velocity, but the position and velocity is a function of time. Okay? So that will be our analogy later on. Now, so as we can see, the new functional integral is a function of functional parameter in alpha. Okay? Now, how do we get the extremum value? To get the extremum value, what do we do? Just like in calculus, what do we do in order to get that extremum value? We get the derivative, then
Set to 0.
We set that derivative to 0, and that is exactly what we're going to do. Okay? So here, because j is a functional parameter of alpha, but also a functional parameter of x, but we want to minimize j in terms of alpha. Okay? So we're not going to take the full derivative, but we're only going to get the partial derivative of this integral with respect to alpha. And then we're going to approach alpha to 0, and we equate this to 0. Okay? You follow? So what does it mean? It means that j is independent of alpha in first order. Along the path, giving the extreme value where alpha is equal to 0. This is for all functions of y x. Of all x. Okay? So whatever that new x is, we don't care. Okay? Because what we're going to vary is the alpha. And that is what we're going to approach. Okay? Questions? Okay. So